Yes. Hello. Thank you for coming here in such large numbers. I'm not very used to talk in front of such a big audience, so bear with me. Let's see how it goes. Today, I would like to talk about level order book, and I would like to have this talk interactive. So feel free to interrupt me whenever you have a question or a comment or any idea I want to share. So my name is Petr Filipský, and I've been working in QMiners C++ team for 7 years now. And I've packed a lot of material into the slides, so let's dive right in. Okay, let's look at the agenda. I would like to start with an overview of limit order, then mention some possible implementations, some data structures for that, with their pros and cons. Then I will show a data analysis from real trading to create some meaningful benchmark. And then we'll get into the actual case study, the design of the structure itself. And then we'll wrap up with some hardware-based optimizations, making the structure friendly for caches, prefetcher, and SIMD instructions. And by the end of this presentation, I hope you'll have a reusable playbook for designing complex data structures for modern hardware, not just in finance, but in any performance-oriented field. All right, let's start with the basics. What is limit order book?
You don't share the screen.
The screen is not shared. Okay. Better now?
Yes.
Great, thanks. All right, so this is some simplified schema of a limit order book, which is an essential data structure used in electronic trading. You can imagine it as a constant flow of limit orders, buy or sell orders for a single security, be it a stock or a futures contract or any other traded asset. And here you can see, sorry, you can see two. You can see two sides here. Here is a bid. On the left is a bid or buy side, where buyers are saying, okay, I'm willing to buy this much at this price. And on the right side, you can see ask side, where sellers are saying, I'm willing to sell at this price. And those bars, those are individual limit orders. So, for example, in this case, a seller is saying, okay, if this price is met, I'm willing to sell. Then you can see that the prices are discrete. There is a grid. The minimal price movements are called ticks or tick size, like 1 cent or a fraction of a cent. And orders are ordered. It means that if there is more than one order at a particular price, they form a queue, and they are ordered typically based on the arrival time. So it's called price time priority. It means that the better price wins, and if there is a tie, the order coming in first wins. Okay, and note that this is a view of just a single contract, but in reality there are many of those, and it depends on it's engineering choice whether we want to store all the contracts in a single storage or separate them. So it's part of the engineering task. Okay, so now you know what the limit order is, and maybe you can say what data structure would you use? What is a good data structure for that? Any ideas? Okay.
Some kind of price normalization would probably work.
Yeah, could work. Okay, so maybe we can proceed to the overview slide where we list some possibilities. The first one, I would say it's a canonical example, canonical implementation. It's a fast hash lookup. So we want to look up a price level based on the price very fast. So there is a hash table, and then we want to enumerate over the levels from best to worst. So for that, we can form sorted linked list. The advantage is the fast lookup and fast delete, but insertion is a bit slower because you have to find a proper place where to insert a new level. And the enumeration is not particularly cache friendly because you are basically hopping over random addresses, and prefetcher cannot help you much. So then there are some tree-based structures, like the heap could fall into this category as well. There are red-black trees, AVL trees. They provide a balanced depth, so lookup time is logarithmic, and they are nice for next and previous price enumeration, but not particularly cache friendly because they are typically node-based. Maybe B trees are trying to address that. And there are splay trees. They have a nice property that they are self-adapting, but for our purpose, maybe they are too heavy. And then there is a plain sorted vector, which has excellent memory locality. It has a logarithmic lookup, but during the enumeration, it can really shine. But insertions and deletions of levels are a bit costly because we have to shift subsequent items in the vector, but it may be a good choice. And then there is a buckets and bit set. It means that there is a vector which is directly accessed. The price is converted to an index, and we are accessing the particular price level directly. But for sparse books, it may not be a good choice because there are a lot of empty levels, and then when we enumerate over them, for example, we have to skip them over and not using cache very efficiently, and we have to use, for example, bit set for excluding empty levels or something like that. So those are the choices I picked. Maybe there are other possibilities. So our goal is to find some best combination of those properties. In more detail, I can show you the canonical example, the hash table with linked list combination. It means that there is a hash table there. Key is some triplet, contract ID, site, and price. And then you calculate the hash, compute in bucket index, and then you are directly accessing a particular price level. But the table is unordered in a sense that you cannot get a proper order from best to worst price. So you have to form some linked list between the levels. And then you have the issue with pointer chasing and also linear insertion. But yeah, and there are more than one contract, obviously. So it looks like something like this, and it's a solid choice. It's typically this is used. All right. So before we jump into choosing a structure, we need to measure how the order book is actually used in real trading. So instead of guessing, I tried to log every book access over a full trading day of some rather small product we trade. And that gives me some real world access patterns, and I can base a benchmark on top of that and experiment with different implementations. And that is what I would like to present here. So the goal is obviously to optimize for what really happens in the market, not just what we imagine might happen theoretically. All right, so I have instrumented the system and logged every book access for a sample day. And it leads to roughly 20 gigabytes of log file, 300 million messages. And the individual messages look like something like this. You can see timestamp, pointer to the flat book or book instance. There are several instances in Trader, so that's interesting to slice the log for individual instances. Then you can see method name, contract ID, site, price, and the resulting position index and size of the map at the moment of a particular method call. And we can split the log by instance. Then you can see that the hottest book has 230 millions of accesses, and the second one 41, and so on. So there is a dominant book there. And here is what is actually called most. So I split the log based on the method name. You can see that most of the calls is the get best method. It means that we are directly jumping to a best level. So that's interesting because the lookups themselves are much less frequent. So we have to have direct access to best level. It makes sense because most of the interesting things happen near the best levels. So the second one is get, and the third one is next. It means enumeration from some level to a next and next and next. And then there is an attempt to create a new level. These are all attempts, so it's, I don't know, 2 million of attempts, but resulting in an actual insertion of a level, because mostly the level already exists. So the actual insert, there's only 30,000 of them, and similar numbers of erases. That's logical. And then there are allocations, but it's implementation specific. So that's interesting because insertions and erase is I don't know, three orders of magnitude lower than the lookups. So the workload is read heavy and has huge bias towards the best of book. Because when we look, okay, one more thing, that when you look at a different instance of the book, the histogram looks different. So it depends, and there are different use cases, obviously. But when we look at okay, there are many contracts. So I picked the most liquid one, and then we can see that the get is the mostly called method. It has 1.2 million of lookups and 900,000 of calls of get best. Okay, in total there is, yeah, that's it. And then I tried to make a histogram of resulting positions. If we are looking up based on a price, what actual index we get. So you can see that the dominant one is again the best level, and the top two are together. I don't know. Here I have a accumulated histogram. So 90% of the lookups is top two levels, and 95% of lookups are in top 3 levels. So it makes perfect sense because if we are trading, most actions happen near the best levels. So it's nice. And the size is relatively small. In the case of the product I picked, it's around 20 levels. So the books are very small and the lookups are near the best level. Yes?
So 2 questions. So position here means that you are basically asking what's the best price for this contract? And then and position one means you are asking what's the second best price?
You mean these two rows? It means that you are looking a level based on a price, and you don't know what level it is, and as a result, you get, in this case, the best level. In this case,
so you look by price, and it says 920,000 times I looked at the best one. Okay.
Yes. So you could, in this case, you could call get best, but the client code doesn't know it, right? It just looks up based on a price and gets the best level. Okay, so the takeaway is that we could possibly beat a hash table, because in this access pattern, it's not that important to have a really constant random lookup, right? Because we are looking up levels near the best level typically. Okay, so I tried to create some benchmark. So I created random keys. I used random generator and uniform real distribution for uniformly distributed random keys. That's the worst price in our scenario. And then I use discrete distribution, which is parameterized by weights. And those weights, those numbers here, they are directly used from the histogram, which was collected here. So that means that I have a set of random keys which follow the same distribution like in the real world. So as a result, hopefully I get a real world like benchmark. And in order to have the runs repeatable, I create the lookup keys up front, and then I'm using them to different data structures. That's obvious. Okay, so let's start with some baseline benchmark. I'm benchmarking third-party maps. I'm using Boost and STD maps. So Boost unordered flat map, it's very fast hash map. It uses open addressing, and you can see that that's mostly the fastest one. Then I'm using STD unordered map, which has close addressing. It's not that fast, but pretty good. And then I'm using tree-based structures like STD map. It's typically implemented as red black tree, and Boost map, which can be parameterized. So I used red black tree structure and AVL tree and splay tree. And then I'm testing flat maps, STD flat map and Boost flat map. The difference between those two is that STD flat map has two vectors. It keeps separately keys from values, while the Boost flat map has a single vector of pairs. So you can see that the unordered flat map is the winner in most cases. Only the enumeration is where the flat map really shines. That's as expected. And it's worth to mention that the enumeration over the unordered maps, it's not fair comparison, because in this case we are enumerating the order the container itself gives us, and that's not the interesting order, right? So in case of unordered maps, we would have to create a linked list and follow the order we are interested in, which is from best to worst price. So keep it in mind that this number is basically meaningless. It just gives us locality numbers, but not very interesting ones. Okay.
Yeah. So sorry, one question. Did you check why splay tree is so bad at find hotkeys?
No, unfortunately, no. I think maybe they are self-adapting, and that maybe the reason is that they have a complicated logic. During the lookup, they modify their internal state, and for this small map, maybe the overhead is simply too high. But I didn't check it thoroughly. So okay, because I picked as a baseline, I picked the unordered flat map and tried to beat it and basically discarded the rest.
There's one more question.
Okay.
Yeah, I wanted to ask, the map size was 21.
Yes. 21 levels overall.
So it was not just 21 elements, right? Or
Yes, it's 21 elements, and you are looking up.
yeah, but that isn't like too little for some more meaningful result, because basically I would benchmark this even against the like linear search through vector.
Yeah, exactly. But that's what the real world data are, right?
Yeah,
You know,
but in that case, why don't you use SIMD to search for it?
we'll get there. But yeah, that was the benchmark was 10 million of operations, the create operations, insertions, deletions. It means that the update here is that we are looking up an existing level, deleting it, and then inserting a new level at the same place. And enumeration was get best, and then next over the container, and lookups. They are basically price-based lookups based on random keys, hotkeys, and fixed keys. And the number of lookup operations is 10 million. Yeah, it's okay. Maybe I proceed to the next benchmark, and yeah, it's there. I call it fixed keys. It means that 10 million times I am hammering a single index like 0, 1, and so on. So in this case, it's obvious that we are not dealing with cache misses, branch mispredictions, and stuff like that. Okay, branch mispredictions maybe yes in case of the logarithmic, binary lookup, but in case of the unordered set lookups, there are no branch misses and so on, because we are just looking up a single index again and again. So this is just the raw instruction speed, right? So without the other effects. I have a lot of bonus slides with measuring other effects like branch mispredictions and cache misses, but this is just a raw instruction speed. In case of more complex measurement, typically the measurement looks something like this. There is some dominant speed, and then there is a long tail of slower cases, and then you have to understand why they are there, and typically they are because of misprediction or cache miss or something like that. But that's not what we are dealing here. This is just a very simple benchmark. Okay, so this is the best one. We can see that the unordered map from STD is almost twice as slow. And this boost unordered flat map is considered to be really very fast hash lookup table. So we pick this as our benchmark or baseline, and we will try to beat it. Okay, so we would like to get the best of both worlds, right? We want very fast lookups. We will try to beat the very well optimized hash table for lookups. And at the same time, we want very fast enumeration over memory and keep the price levels in a sequence we are interested in. So that's the goal. And obviously the vector, very simple structure, will be usable in this scenario.
Can't we also use concurrent data structures and parallelize them?
Yeah, it's mostly out of I would say that it's out of scope of this talk. I mentioned it in only one context, that for individual contracts, for example, we will keep individual vectors of price levels, and we could, for example, shard it based on contract ID, because those are separate vectors. We could split it here and deal with them in parallel with individual vector instances, but that's typically it. when you are inside a single contract, you are looking up just in one thread. Okay, so this is the plan, or this is the organization of memory. There are vectors. This is bit and ask side, and there are several contracts. We have a vector of contracts, and each contract will contain somehow the price-based lookup map. Okay, so from now on we can focus on just a single contract, and we typically want to split it to two vectors, because in this case we have a problem that when we are inserting here, we have to shift all the subsequent items. So if we split it to two vectors, then it's much better, because we can organize the data in a way that the best level is at the end of the vector, and then we are just pushing or popping back of the vector, which is a constant operation. And if we in some case have to insert into the middle of the vector, that's not a big deal, because in such case we are not latency sensitive anyway, and the vector is relatively small, so the penalty is not so high. But this organization with the best level towards the end is crucial for performance. So we have to orient it this way. Okay, another thing is that we want to exploit. Yeah, okay, I have the animation that when the spread narrows like this, we just push back again, and so on, and pop back, and so on. So this is what we want. Another important point is that the prices are discrete, so we want to exploit that. We don't want to deal with floating point prices, so we convert the price to an integer. We have a tick size, so we can divide it by tick size, or better, multiply it by inverse tick size. So all prices are integral. We can use int32 keys. In that case, we get 16 of such keys to a single cache line. We could consider 16 keys, but then we are limited by 64 keys of levels, which for some volatile market, it might not be good enough. So I stick with 32-bit keys. Okay, then on some markets there are dense books, and on others there are sparse books. It means that there are a lot of empty levels. So with dense book, as I already mentioned, the bucket and bit set implementation, we can take a price, maintain some base price, and calculate the index, the offset to the vector directly. Then we have O1 indexing. But that's not too general, because in case of empty levels, the map or the vector would be too big. So more general approach is to maintain just non-empty levels, and then we cannot use the direct indexing, but the prices are sorted, so we can look up with binary search or sequentially. Okay, then there is one more issue we have to address, and that's that when you look at the prices for bit side, they are ascending, right? While they are descending for the ask side. So the straightforward way to solve this would be to have two instances of the map and have a template parameter comparator, use std less for bit and std greater for ask. So we have here we have a lookup. So we look up the contract and then convert the price to integral price, and then based on the side we pick the ask or the bit side. The issue is that this is extremely unpredictable branch, right? Because Those are basically random data coming from the market, and no predictor in the world can predict this. So there is another approach, because we are already converting the prices to integral prices, and we can use the sign. Keys can be signed, and we can calculate the sign like this. It's branchless. 2 times the side minus 1. So it means that we get +1 for ask and -1 for bid. So we have just a single implementation. There's no need to have 2 different types. So we can store the implementations to the array of 2 items and use the Boolean as an index for looking up the proper side. So this way, the code is completely branchless, and also it's friendly for instruction cache, because we have just half of the generated code. There is no template bloat. Okay, so let's overview the whole reverse flat map structure. We keep keys separately from the values. So as I said, we fit 16 keys to a single cache line. We are looking up from the back, and here are the values which only when we find a proper offset, then when we pick up the corresponding value. So this keeps everything cache friendly. It keeps it separated. The keys are very, very compact. Okay, so I tried to prepare several implementations. There is a binary lookup based on STD lower bound, then branchless lower bound, which multiplies this offset based on the comparator result, so it doesn't contain any branches. Then reverse sequential lookup, implemented as find if on top of the reverse iterator. And then I created a handwritten loop, which the generated assembly looked very nice and very readable and simple. So I thought at first that it could be much faster than the implementation of find if with the reverse iterator, but it's not the case. So those are the implementation I prepared. There are compiler explorer links. We will share the slides so you can look at the generated assembly. And the last my favorite implementation is based on the vectorized intrinsics. So maybe we can go through the code. So here is a scalar key. Let's say that it's 104. Here is a broadcast to the vector variable, 16 keys at a time. So we broadcast the number. Then starts the loop. That loop crunches 16 keys at one iteration. Here we load 16 values. You see that the load is unaligned. That we could align the data of the vector to a higher alignment, but the issue is that we are looking up from the back, so it would be unaligned anyway, or maybe it could be done, but it would complicate the code. So I stick with the unaligned load, and on Intel architecture it shouldn't be much slower. Okay, so then we call the greater than compare, and we get a 16 bits mask from that. Note that those 3 zeros correspond to those 3 values. It's swapped. And then we cast it to 32-bit and count number of zeros and do a simple calculation. So we get the index 13. So this way we search 16 keys at a time, and hopefully in just one loop we find the proper position. Okay, so let's look at the benchmark, the same benchmark. Here is a creation, not very interesting. The random update, all the others except the baseline, the hash map, they are very slow. But for updates or hotkeys, it's much better. And the enumeration is as expected. All the implementations are faster than the meaningless enumeration of hash map. And for random keys, not great, but for hotkeys, it looks very, very good. And also for fixed keys. Maybe I would mention the branchless binary lookup. It's not the fastest, but you can see that it's very stable. It basically doesn't care what indices it gets. Every time it has the same speed. So it's a very nice property in some real-time systems that you have guaranteed performance. Okay, I have also implemented not only AVX 512, but also AVX2. So there are two vectorized implementations. And when you look in more detail, you can see that for hotkeys, it means for real-world keys, we can see in trading day of our product, we beat the hash lookup. Okay, this is the fixed keys benchmark. So we just few interesting facts. Here is the branchless binary lookup. So you can see it's not very fast, but really stable, just like the hash lookup. And then here the pink line, it's the AVX 512. You can see that first 16 keys, it's basically constant, and then it goes linearly up. And for AVX2, you can see that there is a one step at index 8. And maybe I mentioned the handwritten loop. It's this purple one. So maybe at the beginning it's a bit faster than the STL algorithm, but it doesn't scale very well. So it's a good idea to use STL algorithms over the handwritten loops, as we can see here. And here is the branchful binary lookup that's very similar to the implementations we have seen in the baseline benchmark. Okay, and here are the lines. It's for the result for hotkeys. So you can see that in this case we beat the hash map. Okay, so the vectorized instructions using intrinsics, not very portable code, not nice. You have to pick a proper type, proper extension. So that's why it's the fastest, but not great. But there is great news. In C++26, there is upcoming SIMD standard SIMD support. So with that, you can use basically any arithmetic types, be it signed or unsigned, integers or floats. I tried some of them. I tried also 128-bit variables. They compile, but they didn't get vectorized, so they are great out here, but maybe they will support it as well. You also get the support of all lane sizes from 512 down to 32 bits. And you should get a support for many extensions in future, not only AVX, but for example, ARM, SV, or WebAssembly. So that sounds great. And let's look at the code. So here is the generic version of the same implementation, no macros and generic code. So here you can see that it's just a templated by a key, and you can use either floating point or integral numbers. Then there is non-type template parameter width and tag, which represents alignment. So you get the types generically, and then we have a broadcast. It's a simple assignment of a scalar value to a vector value. Then we have a loop going next width every time. I used attribute likely because I believe that we find the key at first loop, first iteration. Yes.
Well, there were making some tests to ensure does the likely attribute doing various compilers, and found that in some compilers it does nothing. In other compilers it sets the probability to 90% and the code optimizes it accordingly, which may be good, may not be good, but if you believe it will be there with the after 90% change, it's okay. But actually it may be more accurate and actually gives 99% or something like that, and in that case likely is not perfect.
Yeah, sure.
I read that profile guided optimization, which is some kind of compiler trickery, you can just iterate without having to rely on this bit. Just that in practice is more like try and see, experiment with it, maybe it will help.
You have to definitely check the generated assembly if that does what you want. That's one thing. Another thing is that the good thing is that you have it in the code. So even for programmer, it's a good piece of information. And the third thing is that profile guided optimization is not very good choice for some scenarios. For example, in trading, you have a lot of conditions which you are basically waiting for some particular event, and you have a condition which is mostly false. And then when it's true, you want to be the fastest. But when you are using profile guided optimization, you get exactly the opposite behavior than you are looking for, right?
Profile based on the data that you expect, so you make sure.
Yeah, but still, you have 99 times out of the 100, you get the false condition, and then you have one, for example, the price accent some border, and then you want to act, right? And in that case, you are the slowest because it's the less probable. Maybe we can postpone this discussion to later.
Actually, do have a question about this. So the lookups were heavily dominated by the zero level, like best. Right? Have you tried some terrible hack like before starting ADX 512, which has significant penalty to get started? Have you tried just looking at the first index? And
I tried that, and I think the penalty is not that big when we get back to the benchmark. You can see that this is the simple, sorry, the purple one is the simple sequential lookup, right? And this one is the vectorized one. So still you don't see some constant penalty on the vectorized version, at least at this benchmark. Yeah, but sure, many experiments may be done, and maybe you can find some hybrid between vectorized and not a vectorized version. But one goal is to get the smallest code, right, to fit to cache and have as few branches as possible. And this is one way to do it. I'm not saying that it's the best one. Okay, so we have this. Any more questions? Okay, we can proceed. So this is when you get the bit mask from the comparison greater than, you just can use this operator, and you get a proper width bit mask out of that. And then the bit mask in the standard, it's an opaque type. You cannot cast it or count zeros or something like that to make it generic. So you can use predicates like any of and find last set or something like that. Okay, so that's the equivalent code. And on top of that, you can even build some cascade, like you can search 16 keys at a time. And then when there are no more than 16 keys, you can proceed to searching 8 and 4 and so on. So you can create some compile time recursion loop like this. And then you have a scalar tail. Okay, let's look at the generated assembly layout. This is not very good visible, but just as a bulk, this is AVX. So it's 128 bit registers. This is version for AVX2, and this is version of AVX 512. So the same code, the same generic code generates the assembly based on the extension you pick. And when I highlight the hottest path, that's the likely path, you can see that you get 15 instructions which are kept together. So there is no jump, all is in single sequence. So in this case, the likely, at least it didn't do anything wrong. So those 15 instructions you can see in LLVM MCA, machine code analyzer. You can see how it's on the AMD machine, how it's processed, that it's processed in parallel. Those are vectorized instructions, and also they are decoded in parallel and so on. So in this case, we get 16 clock cycles latency, at least based on this static analysis. And when we look,
question.
Yes.
So first, what tool did you use for the visualization of the assembly blocks?
I use Compiler Explorer. If you open this link, you can see it there. It's part of the workspace there. So you can open it there. You have it's called assembly layout or layout graph or something like that. And also you can open the MCA tool where you see a detection of bottlenecks and stuff like that.
It's very useful. Good. And second question, sorry. You said that this is on AMD machine?
I tested it on AMD
okay.
Epic.
Yeah, the new AMDs don't have AVX, so penalty. They just go with full speed.
Okay, maybe on Intel I would get different results. Yeah, for MCA you can put on the command line, you can put an architecture of your choice, and you get the corresponding. So probably there you would see something worse than this.
I found that the architecture optimization it's not really optimal for the architecture set there. In practice, I found that for AMD Zen 5, putting their Meteor Lake makes it like 10% faster sometimes. Doesn't make any sense, but it's just faster if you sell it to Intel Meteor Lake or AMD Zen 5.
Okay. Okay, so let's look at the benchmark. There are SIMD variants, 16, 8, 4, 2, and 1. So you can use even 1. It's basically equivalent to the scalar code. AVX 512 or SIMD 16 and 8, they are same like AVX 512 and AVX 2. We have additional SIMD 4 here, so it corresponds to AVX. I didn't implement it AVX version in intrinsics, so we can see it here. The steps for keys at a time, and the worst one I would say is the SIMD2. Maybe we see some overhead here. That's why in the cascade here I use this condition. So when we are below 4, we just go for scalar code. Okay, and here is the hot keys benchmark. Okay, so what time we have? Good. So the summary is it's good idea to start with reality, measure what really matters in your use case. don't guess, but instrument your system and log real-world access patterns and work with that. Establish a baseline you compare to, so that if you pick a strong option, you challenge yourself and it takes some time to be better, at least for your particular data. So I really understand that the hash table is much more generic approach, right? So the goal is not to beat it in general, because there's a lot of effort put into that, but it's possible for a particular use case to be better with much less effort. And pick the right tool for the job, make predictable memory layout, very simple structures, not anything fancy, just vectors. And optimize for the hardware. Know your cache line, know your prefetcher, know branch predictor, use SIMD where it makes sense, and measure. And respect constants. For big N, it definitely makes sense to use asymptotics, but for very small maps, you can beat O1 algorithm with ON when it has very low constants. And choose for locality, design for hardware, and verify with data. Do a lot of benchmarking. So that's it. Here are the links I used for the talk. And if you have any questions, and then I have a lot of bonus slides, so we can dive in it if there's time, but no pressure.
So you said that you started with basically gathering data from production to see how what you should optimize for. Did you then observe the performance in production when you deployed this version, or was this just toy?
At this stage, it's just a toy. I would have to do much more measurements before we maybe hope for getting it to production. It's definitely not the production ready code. It was just I had the idea for a long time, and this forced me to more elaborate around that, but it's not production ready at all. Okay, so do you mind if I fly through? Maybe I can show you one measurement which demonstrates the branch predictor penalty from, as we mentioned, the branchful and branchless version of the side lookup. Okay, so this is the PMR, polymorphic memory resource used for more compact memory layout. Here is a value pool for deleting and inserting the values back, because we want to preserve a secondary capacity. For example, if you have this value and you have a nested vector, you don't lose the capacity of that vector. So you can use a pool shared between many map instances. This cache miss. This is open versus close addressing, solving of collisions of hash tables. And now here is a CPU pipeline. When you have an instruction, it has several phases: fetch, decode, execute, write back. We already seen it in the MCA analyzer, something like that. So if it was sequential, it looks like something like that, but you don't want to waste the units. So when you fetch one instruction, you decode it, and at that time you can fetch another instruction and so on. So we have a superscalar pipeline. But the problematic part is the branches, right? If this is a conditional jump and it results in jump to N, so instruction N, but branch predictor predicts that it will not jump, then you are processing speculatively the next instructions. And then when the condition is evaluated finally, and you realize that you didn't jump and should have to, you have to roll back all this, and the performance goes down. There is a pipeline bubble, so-called. So we can look at this, how it looks in practice. This is a perf measurement. You can see there is some number of lookups. It doesn't directly correspond to the benchmark we already seen. So the resulting lookups, they are in 0.7 seconds, right? So this is the branchless version. We are converting the price, calculating the sign, and using the site as an offset to the map array. So it's completely branchless. And we get to, it's 8.4 billions of instructions, and we get to 3.14 instructions per cycle. And so this is the final version, and this is the branchful version. From 0.7 we get to 1.1 basically. The number of instructions per cycle goes down to 2. And why is that? Here is number of branches, right? So in the previous case, we got 614 millions of branches, and this time we get 814. So there are 200 of millions of additional branches. And in the first case, there's tiny number of branch misses, and in this case, there are hundreds of millions of branch misses. So exactly half of the additional branches was mispredicted, which led to this high number and this low number. That's basically it. So Linux perf is a great tool which is able to give you insights like this, that you are on a good path in designing your structure. When there are no branches, there are no pipeline bubbles. Okay, maybe that's it. Okay, thank you very much.